Hello and welcome to the course Basics of Experiment Design for Cognitive Psychologists. I am Dr. Ark Verma from the Department of Cognitive Science at IIT Kanpur. As you've seen in the introduction lecture, we are going to talk about various aspects of experimental design and the quantitative method in cognitive psychology in this course. But before I start with those things, I thought it might be a good idea to basically give us a background, give us a bit of a context about what experimental design is all about, where do the principles of experimental design derive from, and related facts that are important not only in terms of measurement in in psychology or cognitive psychology, but also generally. So we will discuss in this and a couple of other lectures about the basic principles of what basically makes the scientific method, where are these principles coming from, and so on. So this week is going to be a little bit about a brief historical background and some of the things that I just mentioned. Let's first begin talking about the scientific method. All of us have heard this term, the scientific method, a number of times, and some of us probably are still wondering what this scientific method is all about. Is it just collecting data, coming up with observations and basically saying, okay, this is correct, this is not, and so on. Let's talk a little bit about where this scientific method really come from. Now, the advent of psychology as a scientific discipline carries a lot of stories about the internal struggles amongst the psychologists themselves to basically adopt a particular kind of method to get themselves categorized as a science. One of the initial anxieties of psychologists probably has been, this thing of calling themselves as a genuine bona fide science, much like, let's say, the physics and the chemistry, and slightly different from only philosophical or analytical traditions. So this is something that has occupied the minds of scientists or psychologists a lot, and let us try and see where is this really coming from. Now, what do you call science? What do we say? For example, if we were to talk about basic definitions, where do we sort of draw a line and say, oh, this is scientific, this is what is called science, and this is not? So traditionally, the scientific method or science can be looked upon as a continuous accumulation of facts based on objective and, importantly, value-free observation and experimentation. So all of the knowledge that we are gaining through objective methods of observation, which are value-free, which are not afflicted by our judgments of what is right and what is wrong, what do we like, what do we not like, what aligns with our ideology, what does not align with our ideology. Science, in some sense, in that sense, you can see, is a sterile observation of facts which can be later verified and woven in form of a theoretical framework. So let us say that is a loose definition of science that we will start with. Now, interestingly, this preoccupation with the definition of science or what scientific method is all about is broadly, if you see, absent with a lot of scientists themselves. They prefer talking more about what they do rather than dwelling about the underlying principles. More often than not, the underlying principles of scientific inquiry are taken for granted. It is basically assume that we are all following this scientific tradition, the tradition of the particular method, let us say the hypothetico-deductive model, or hypothesis testing and so on. But it's rather seldom and probably only in courses of research methods and research designs that we wonder and we talk about the underlying principles of this scientific method. I'll make an attempt to very briefly cover some of these things as we go ahead in this week. Now, where does this all start? As with most disciplines, it starts, in ancient Greek, where there were thinkers and, scientists like Plato and Aristotle. So Plato basically says that reasoning or gaining of knowledge is something that is innate. It comes within us. It is something that we are endowed with to a certain extent. So Plato thinks that knowledge is endowed by the soul. Okay, when the soul enters the body, it brings with itself some kind of knowledge, some kind of the ability to distinguish between what is correct and what is incorrect. In that respect, scientific knowledge, or any knowledge for that matter, does not really require careful and objective observation. Rather, it rests within innate reasoning and endowed intelligence. We are endowed intelligent beings, so we should know what is right, what is not. We do not need to scrutinize what we know, we do not need to verify what we think is correct. Rather, the tendency is to believe that, okay, we are endowed beings, children of the creator, and we know what is correct and what is not. There are other methods, for example, however, say for example, people like Aristotle have distinguished between different modes of arriving at knowledge or reasoning. Let's look at that for a little bit. For example, Aristotle distinguishes between deductive and inductive reasoning. What is deductive reasoning? Deductive reasoning basically starts from indisputable principles, things that you have observed yourself, let us say first-hand observations, which we know that are true conclusions. These are new, maybe these are true conclusions, and new facts can be derived from these observations following the rules of logic. For example, consider the statement, all humans are mortal. Now, you start with all humans are mortal, Rajesh is human. What will be the conclusion be? The conclusion will be Rajesh is also mortal. So basically, if you take premises A and B and you follow the correct principle of logical reasoning, premise C, or basically the conclusion C, is automatically drawn from premises A and B. That is an example, sort of a crude example for deductive reasoning. What is inductive reasoning? Inductive reasoning basically starts from a series of converging observations, lots of observation picked over time, and these observations are used to arrive at a general conclusion. It is typically one of the dominant methods in science to arrive at these scientific laws using observed phenomena. We will talk about this in more detail in the next few lectures. Take for example these statements. The sun has risen in the east every day of my life, so I know that to be true. The sun rose in the east yesterday, the sun rose in the east day before, probably today itself. So we have this third statement, the sun rose in the east today. Now, if we have this bundle of observations, we can conclude from this bundle of observations that the sun rises in the east every day. So on the basis of these specific observations, that the sun has risen in the east every day of my life, the sun has risen in the east yesterday and the day before, and even today the sun has risen in the east. So we can basically put these 3 or 4 observations together, and we can conclude from this that the sun rises in the east every day. Alright. So this is again on the basis of certain observations we have arrived at a conclusion, and we assume that conclusion is correct. Take another example. For instance, in a set of clinical trials, let's say A, 90% of the patients who took drug A recovered from the disease Z. So, there was a set of clinical trials, a particular drug was administered, and 90% of the patients who took this drug, drug A, recovered from whatever disease we are calling as Z. Another statement is, in study B, 80% of the patients reported a reduction in the symptoms of the disease Z when given drug A. Let's look at another study. In a third study, 85% of a diverse group of patients who were given the drug A experienced relief from the ailments accompanying disease Z. So now, across a set of 3 different studies, maybe conducted in different parts of the world by different scientists, by different research groups, we have some evidence that says when the drug A is administered, people experience relief from the disease Z. So on the basis of putting together these 3 different studies, we can actually conclude that drug A is likely an effective drug for treating patients with disease Z. Alright. So this is another example of how inductive reasoning may be used to come up with scientific conclusions. Now, notice the subtle differences in the two. In both cases, we have premises and we have conclusions, but notice there is something interesting happening in deductive reasoning. In deductive reasoning, the conclusions are guaranteed to be true if the logical premises, if the logical rules are correct, logical rules are followed. Inductive reasoning, however, does not guarantee that whatever conclusions you are taking out are basically correct, because it depends on a number of factors. It depends upon the quality of observations, it depends upon the methods being followed, and so on. Alright. So, inductive reasoning therefore is more steeped in rationalism, according to which reality can be known by reasoning. Now, here we are reasoning deriving from innate knowledge, and it's basically most used in more common deductions in daily life. The conclusions and the generalizations that we are sort of building upon in the case of inductive reasoning are also drawn from a limited set of observations. Say for example, if one were to say that all swans are white, there is no way to get and measure or say for example come across all the swans that are present in this world. We see one swan, we see two, we see 10, we see 20, and the basis of this we basically concluded, okay, probably all swans are white, something like that. Okay, this is the kind of reasoning we also adopt in daily life when we notice the similarities between events and experiences, and on the basis of those observations we formulate general principles about how the world works. Alright, such reasoning is typically emphasized in empiricism, according to which knowledge is based on observation and experimentation. So, you observe something, you experiment, maybe formulate some hypotheses, test them, and basically come up with knowledge to explain whatever observed phenomena are there. Now, for the most part, both inductive and deductive methods of reasoning have been used as sources of knowledge. So, they are both well accepted, well practiced ways of getting at knowledge. But if we carefully compare the two modes of gaining knowledge, deductive and inductive reasoning, it seems that inductive reasoning may underlie the nature of scientific thought and the scientific method. It was championed, however, say for example by British scholar Francis Bacon, who opined that knowledge mainly should be based on careful empirical observations and not on authority. See, a lot of times the premises that are that form the basis or foundation of deductive reasoning or deductive knowledge are based on authority. Authority of, say for example, somebody who is considered an expert, somebody who is considered, say for example, in cases like say for example engineering. So, there are godmen, there are holy books which will say this is how things are, and then you have to accept them. Francis Bacon and people like him basically said that knowledge should be based not on authority but on careful empirical observation. Bacon advocated that we should document experimental histories in a systematic manner, which are systematic observations where critical elements could be actively manipulated and their effects studied. So, if you have a premise, if you have an observation, if you want to take out a conclusion, before taking out a conclusion you manipulate things, you basically look at their effects before you derive or before you arrive at some kind of conclusions about these things. This tradition of where does knowledge come from and what are the correct sources of knowledge is basically what is the broad subject matter of the subject of this field called philosophy of science. Now, in early 20th century, philosophers basically shifted their attention from metaphysical questions to questions about the nature and the methodology of the scientific approach. This was taken up by several scholars in Vienna around that time in the early 19th, late 19th and early 20th century. People like Moritz Schlick and others like Rudolf Carnap and Ludwig Wittgenstein, among others, which were together referred to as the Vienna Circle. This movement that starts roughly around this time is referred to as the logical positivist movement. Let's talk a little bit about this to understand the context and the history of the scientific method. Now, what is logical positivism? The logical part of this definition or the logical part of this term logical positivism derives from the preoccupation of the times, basically saying that there is this preoccupation with language and there is this preoccupation with where does meaning come from. So, logic is supposed to be a method using which we derive meaning, and therefore the logical part of this logical positivism comes from. Positivistic or the positivism part of it basically derives from the high esteem that was associated with the fact that we are talking about scientific knowledge, and in some extent to some extent about the arrogance related to scientific knowledge, that scientific knowledge is the best or the only true form of knowledge. So this is where the movement is termed logical positivism. The way of deriving knowledge and the fact that this knowledge that we are deriving using scientific method or using logical reasoning is the correct and the truest form of knowledge. Now, there is a bunch of things within this logical positivist movement that are interesting, and they basically contribute to the evolution of scientific thought. Let us pay attention to that a little bit. One of the things that logical positivists took in their hands, or were really concerned with, was this idea of demarcation of science. So they're basically concerned a little bit about setting scientific knowledge apart from non-scientific knowledge. So for example, what is non-scientific knowledge? Knowledge that is derived from tradition, from common sense, from belief, faith, etc. How do you distinguish this from scientific knowledge? Why is scientific knowledge superior or special as opposed to the knowledge that is derived from our beliefs or our faith, or even say by the method of authority and so on? So they wanted this definition to be very clear cut. They wanted to be able to say that, okay, this is where scientific knowledge starts, or this is where common sense ends and scientific knowledge begins. All right. Now, logical positivists postulated that science follows through a circle of observation, induction and verification. The underlying assumption is that there is a direct correspondence between reality, how the world is, and human perception, our ability to observe how the world is. The idea somehow is that our means of observing how the world works are in some sense infallible, and once we go through that, once we observe carefully, note down carefully, analyze the workings of the world, we will understand how the world works better, and that will be the best form of knowledge. So once you have these observations, what do? The next step would be to translate these individual observations into general conclusions, some using inductive reasoning, basically which will tell us about how the world works. Okay, so for example, something like how Newton would have arrived at the mathematical laws of physics that eventually could explain the laws of motion that Newton arrived at. Okay, so say for example, we talk about this thing about the apple falling on Newton's head, and what does it basically indicate, and how does he start from there and reach at the laws of gravity and so on. So things like this. This is basically the initial ideas of how scientific knowledge must be generated. The next step in this, once you have made observations, because method of observation is considered sacrosanct, so you've observed a bunch of phenomena, you have translated these observations into general frameworks, or you can say theories that predict how the world works. What is the next and the final step? The final and the most important step would be that you should be able to verify these general conclusions that one has arrived at. So the positivists claimed that experimental verification was one of the important demarcation criteria of scientific knowledge. Scientific knowledge will be built upon knowledge or observation of the facts that can be verified to be true. How will they be verified? They will be verified through experimentation. So you come up with this phenomena, somebody says this is how things are, you go out and verify it. Once you have been able to verify it, that will only then constitute scientific knowledge. Okay, and again, how do you verify it? You verify anything as true or false on the basis of value-free, sterile observation. Okay, so there is a degree of circularity here, which we will address going forward. Now, the logical positivists also accepted deductive reasoning based on the principles of logic as a way of making meaningful statements, but not really as a means of generating new knowledge. Okay, so according to the positivists, or according in the tradition of this logical positivist movement, the idea is that deductive reasoning, which is based on premises and follows logical reasoning and comes up with some conclusions, is good for understanding whatever existing knowledge is there, but it is not the preferred way to generating new knowledge. Okay, for that maybe inductive reasoning would be the preferred method. Now, this is a little bit about the positivist movement. I am not really going into an extreme detail, but I just want to give you a flavor of where things started from. Okay, so let's look at some of the possible critiques of this movement to understand where do things go from here. Now, while the positivists were rather firm with their view of the demarcation criteria, if you zoom in, if you look a bit closely, there could be more nuances to how scientific knowledge must be generated. Let's look at some of these things. Now, scientific knowledge does not automatically proceed from perception to understanding, and even verifiable facts, for example, may lead to erroneous conclusions. This is something that we should keep in mind, and we'll come across several examples along the way to reiterate this fact. Let's take some specific criteria. For example, perception cannot be the final destination. Logical positivists basically assume that the facts could be perceived independently of any theoretical framework. See, what perception or observation of the world tells us are isolated, unconnected facts. And you observe one thing the other day, the other fact the other day, the completely unrelated fact the other day. It is important that we are able to connect these dots. It is important that this scientific knowledge that we are talking about is structured in a particular way. Otherwise, what we will be doing is we will be having random observations across a particular time period, and we will say, okay, this is correct and this is correct and this is correct, but we will not have a framework to connect these dots and to evolve a particular framework within scientific knowledge will function. So, the logical positivists assume that facts could be perceived independently of any theoretical framework and would be the same for all observers. However, it has been pointed out that this may not be the case. Typically, when you start observing things, there is a broader framework under which you will weave or you will be able to connect all these observations. This is slightly different to what the logical positivists were assuming in the beginning. For example, researchers typically observe, and this is also something that researchers typically observe reality in fragments. You see something here, something there, which they must try to stitch together and build a theoretical framework and interpret the facts within that context. So, for example, if you have a theory about how the planetary system works, or you have a theory about how gravity works or how motion works, or say, for example, as we are psychologists, you have a theory about, say, for example, why do people suffer from personality disorders, or say, for example, what causes autism, anything for that matter. You can have certain observations, but those observations have to be seen within a given framework. They are not disconnected, isolated, disorganized facts. So, you need to be able to put them together is what the idea is. Okay, look at this picture, for example. At this point, if you are seeing this picture, you will just see that, okay, these are just fragmented aspects of black and white patterns, but they are not making any sense. How will they make sense? If we have a theory of something, if we have a framework within which we can start looking towards a particular pattern, all of these observations that we are finding from point A to point B, for example, or at different points of time and different places, how do we stitch them together? How do we start seeing a pattern? We will not see a pattern unless we have a framework to look into these findings. So, theories are very important, and a theoretical framework shall provide an element of interpretation to the observed facts. Now, you will start, say, for example, you have a particular theory of motion, or you have a particular theory of how the planetary system works. Once you have that theory in place, you will now start interpreting these isolated findings from the lenses of this theory, and some will sort of go together, some will not, but it will basically give you a way in which to interpret whatever isolated findings or disconnected findings you are observing. Also, having a theory helps in defining the focal points of the inquiry as well. For example, theories typically allow scientists to search and research with focus in specific directions. For example, if you have a theory about how the the Earth and the other planets revolve around the Sun, this particular theory will give you questions, will give you focus as to what are the important questions underlying this theory, and how will we sort of investigate the findings and phenomena within the ambit of this particular theory. So, facts and observations cannot stand alone. They are not isolated, they are not disconnected. They need to be organized and stitched together in some form of a framework, which we can typically at least at this point refer to as a theory. Alright, so let's take some examples about this. Brisbane and Russell in their book, they talk about this example with the famous astronomer Galileo Galilei. They say Galileo initially proposed a method to measure the size of stars, all right, wherein he positioned himself relative to a chord that just blocked a particular star out of sight. He assumed that on the basis of the thickness of whatever cord that is, so a piece of thread, and the distance of the eye from the cord, he will be able to calculate the visual angle subtended by the cord and thus the visual angle subtended by the star, which can eventually be used to determine the overall size of the star. That is the idea, that is what he started with. However, at this point he did not realize that the apparent size of the star appears much bigger than they actually, that the apparent size of the star appears much bigger than they are because of the atmospheric scatter of the light rays, the light rays coming. So the star might be small, but because the light coming from the star is dispersed through the atmosphere, it may appear much bigger than it actually is. And also the fact that stars are at different distances from the Earth, so the relative calculation of size must take into account the distance at which a particular star is from the Earth. So these two are important points, and these 2 points, if ignored or if not factored in, will lead to erroneous calculation of the size of the star. So the measurements of the diameters of the star as derived by this chord method would be worthless if not corrected for these sources of errors. Similarly, a similar example comes from, say, for example, Paul Boyer. Paul Boyer in 1963 published his discovery of a substance called phosphohistidine, which at that time was touted as a substance that was very important in the chemical reactions that provide energy to the cells of the body. Now, interestingly, around 2 decades later, after this publication of the role and the function of phosphohistidine, it was discovered that actually this element, this chemical, served a very different function to what Boyer had initially assumed. In 1981, see, the initial publication was in 63. So Boyer in 1981 admitted that he had been wrong, and he moved on with a new theory of energy provision in cells that did not require the intractable intermediate which he had settled with earlier. And eventually, for this new theory, he was awarded the Nobel Prize for Chemistry in 1997. So you can see that science and scientists are basically rather ready to modify their observations, move on. And it is possible that once you have a theory, the theory allows you to see the initial observations in a different light. Some of them may make sense, some of them may not, some of them will basically fall in very nicely into pieces of a jigsaw that will tell you or help you explain a given phenomena. Alright, look at this now. This is the same picture that we were seeing moments ago. Now, if we have provided it a context, we have provided this picture a background, now you can see that it seems like a picture of a actual female, as opposed to slides ago where we saw this without a proper background. So here it is very difficult to interpret, oh, this is what we are seeing, but once you have a particular kind of a background, let's say a theoretical framework, then you are able to decipher, oh, this is the picture of a female. Another very interesting critique to the positivist stance can be found in the idea that scientific theories typically include also non-observable variables. For example, force is equals to mass into acceleration. None of the variables in this equation can actually directly be perceived by the senses. So the idea that positivism was based on tangible observations being made by people sort of suffers here a little bit. Now, while not in its entirety, but science as proposed by positivists needed to get around this problem of non-observable entities. Positivists initially pointed out that while certain variables cannot be directly perceived by the senses, they could still be quantified and hence measured and have magnitudes measurable in relatively simple ways. For example, mass as weight in grams, acceleration is the rate of change of velocity over time, things like these. The idea was that you would use operational definitions to postulate how a given variable shall be quantified and hence measured within the confines of a given theory, allowing then for the verification of the same. However, this idea of operational definitions does not by itself guarantee that the variables of interest can be easily measured, because you can very well have a very wrong operational definition of something. Let's say you want to measure anger and you have the operational definition of anger as the number of times a person smiles. Now, or something like, let's say for example, number of times a person's heart rate increases or breathing increases and so on. You can come up with various operational definitions, but it is not necessary that those operational definitions are the correct way of quantifying these non-observable entities. So even with operational definitions, it is possible that variables require complex indirect methods to be measured. Alright. So Carnap here points out that the distinction between observables and non-observables may be an arbitrary distinction just as a matter of convention and so on, but again this is something that is a bit of a thorn in the fundamental principles of generating scientific knowledge that are laid down by logical positivists. Also, something that is important in posterity is that non-observables can actually become observable over time by the evolution of technology. For instance, the bolt signal obtained through fMRI can actually be seen as an index of the brain's functioning. Wherever the flow of blood and the oxygen sort of goes in the brain is taken now as an index of that particular area of the brain is engaged in performing a particular cognitive function. So in that sense, while functioning of the brain per se cannot be directly measured, but with the advent of the bolt signal, and there are newer techniques nowadays which can basically act as measures of brain activity. So this is one. Finally, it has been pointed out that it can be logically impossible to verify all the conclusions and prove them to be true beyond doubt. I was giving this example earlier. For instance, while all swans are white seems like a reasonable conclusion for the most part, one can really never go out and verify all of this to be true. It's not possible for you to find every swan in this world, whatever the number be, and basically say that okay, I have verified this particular fact that all swans are white. It cannot be done. So verification in that sense cannot be used as an infallible basis of science. It is an important process, but is it an infallible basis of science is something that can be questioned. Also, conclusions drawn from inductive reasoning are falsifiable with even a single counter example. So maybe we stick with this statement of all swans are white, but somebody brings across us a black swan. By the way, people have found black swans. So as soon as the first counter example is presented, the particular theory is falsified, and hence the validity of whatever that knowledge was basically gets questioned. So verification in that sense, and this is basically the conclusion of this exercise, that verification cannot be the foundation of science, because while it is not possible to verify all the scientific statements, there might be merit to pursue this through falsification. So later theories, and we'll talk about this in the next lecture, basically suggest that verification maybe not, but falsification has to be the basis of scientific knowledge. Alright, so I'll stop here. I'll basically continue the same discussion in the next lecture. Thank you.